So in this video, we're going to look at our last example of analytically ascertaining the domain of a function. And this time we're going to put the square root in the denominator, and we're going to put a quadratic expression in the numerator. And we're going to see this introduces a little bit of nuance to the problem. So here's the function. We have a quadratic expression in the numerator, x squared minus 2x minus 3. And we have a square root function, the square root of 2x minus 3, or a square root expression in the denominator. So when we do this, what we want to recognize is that the numerator can equal 0. It is okay for the numerator to be 0. Okay to be 0. The most common mistake I would see on this type of problem would be a student just saying, hey, this can't be 0. Because in the previous example we looked at, we had a quadratic in the denominator where it couldn't be 0. But the numerator can be 0, so we don't want to worry about that. We don't have any restriction coming at us from the numerator. So we focus on the denominator. And there's two restrictions coming at us out of the denominator. So here's what they are. We have the square root function sitting here in the denominator. And we know that we need the stuff inside the square root to be greater than or equal to 0, or we get negative numbers under the square root function, which gives us answers that are complex but not real numbers. So we're going to need to say, because of the square root function, we need to say, hey, 2x minus 3 has to be greater than or equal to 0. But we have to be more careful than that. So this is the first step. The second step is we need to realize that we have a denominator here. So if 2x minus 3 were to equal 0, what would happen to us? Well, we would wind up getting the square root of 0, which equals 0. And oh no, we would have a 0 in the denominator. So this is a time where usually when we are working with the square root function, usually we say, hey, we need 2x minus 3 to be greater than or equal to 0. That's what we usually say, because we don't want negative numbers under the square root. But now we need to recognize that we can't let 2x minus 3 equal 0, or we get the square root of 0, which causes a division by 0. So our restriction can't have the equal sign on it this time. We need the stuff under here to be a positive real number. 2x minus 3 has to be greater than 0, because if we let it equal 0, we get division by 0. And that's the subtlety in this. Students will forget to take the equal 0 off, and then they're allowing a division by 0 in the function, which we can't do. So we simply say, hey, 2x minus 3 has to be non-negative, so it needs to be greater than or equal to 0. But we need to avoid a 0 in the denominator, so 2x minus 3 has to be strictly greater than 0. And then we solve this for x, so we add 3 to both sides, so we get that 2x has to be greater than 3. And then we divide both sides by 2, so we see that x has to be greater than 3 halves. And now we have everything that we need to do to express this in interval notation. So in interval notation, x would be an element of the interval beginning at 3 halves, but now not including it. We don't have that square bracket on there anymore because we're excluding 3 halves, which would cause division by 0, and go from 3 halves to infinity. And again, to drive this home, if I throw 3 halves in here, let's say I put 3 halves in there, I would get 2 divided by 2 is 1, 1 times 3 is 3, 3 minus 3 is 0, square root of 0 is 0. Now I have a division by 0. So we can't put that square bracket on there and say, hey, it's okay to use 3 halves. It's not. It would cause division by 0.